Student friends, in yesterday's lecture, we studied one of the advantages of negative feedback, and that is increasing stability of the circuit. We proved how stability of the amplifier circuitry increases by applying the negative feedback for the amplifier. We proved it by two ways. One, by proving that gain after feedback is only going to depend upon the feedback factor, and which is independent of parameter variation or temperature or even power supply variation, and thus stability will be there for the amplifier with negative feedback. Another aspect we used, and that is by using the formula for sensitivity. We define the sensitivity without feedback, that is change in gain upon original gain, by using that particular definition. We proved that sensitivity after feedback is less than sensitivity before feedback. And we are aware that if sensitivity is less, stability of the circuit will be more. And after feedback, sensitivity decreases, and that's why the stability will automatically increases. Friends, that's all about the articles which we have covered in the yesterday's lecture. Today we are going to study one more advantages of negative feedback, and that is increasing bandwidth. Dear students, please remember that application of the negative feedback in amplifier increases the bandwidth. Basically, bandwidth means the difference between the upper cutoff frequency and the lower cutoff frequency. We already studied when we studied the frequency response of the different amplifiers. And there we have defined the bandwidth, which is the difference between upper cutoff frequency and that of lower cutoff frequency. And here we are going to study that this difference after negative feedback increases. So that means there is increase in bandwidth. To prove the same, let us consider an amplifier with its lower cutoff frequency f1. Now what is the lower cutoff frequency? Lower cutoff frequency is the frequency in low frequency range at which the voltage gain falls to 0.707 times the mid frequency gain. So that particular frequency we can call it as it is the lower cutoff frequency, and it is denoted by f1. Now at the beginning we are thinking only about the low frequency region. We are aware that entire frequency response of an amplifier is divided into three regions. One is low frequency region, second one is the mid frequency region, and third one is the high frequency region. Today we are interested in the low frequency region, and in that we are interested with the lower cutoff frequency before and after feedback. So that's why we are considering an amplifier with its lower cutoff frequency f1 in low frequency range at which the voltage gain falls to 1 upon root 2 or 0.707 times its mid frequency gain. In this particular low frequency range, the voltage gain at any frequency f in a low frequency range without feedback, means when no feedback is applied at any frequency in the low frequency region, voltage gain is given as AL, as like AV. A for gain, L for low frequency region. The low frequency gain AL equal to AM upon 1 minus Z times F1 upon F. Let me call this as the equation number 1, where AM is the mid frequency gain. This equation we have written by the definition, and the definition is mid frequency gain falls by an amount of, low frequency gain falls by an amount of 0.707 times the mid frequency gain. With this particular definition, we can write AL is equal to AM upon 1 minus J into bracket F1 upon F, where F1 is the lower cutoff frequency and F is the any frequency in a low frequency region. AM is the gain in mid frequency. Similarly, by the formula for gain after feedback, respectively in mid frequency range and also the low frequency range, is given as AMF, as like AVF. A for gain, M for MF for mid frequency. In mid frequency region, the voltage gain is given as AM upon 1 minus K times AM. So this is by definition of formula of gain after feedback, but the terminology used is for mid frequency. Second one is the voltage gain in low frequency region after feedback, that is ALF is equal to AL upon 1 minus K times AL. K is obviously feedback factor, AL is the voltage gain in low frequency region without feedback. ALF is the voltage gain after feedback. Let me call this as the equation number 3. Now putting the value of AL, this value AL from equation number 1 into equation number 3, so as to get ALF equal to, we are substituting the value of AL here and here, so as to get ALF is equal to AM upon 1 minus J times F1 upon F. This value upon 1 minus K into AM upon 1 minus J into F1 upon F. Try to take LCM of this particular denominator so as to write AM upon 1 minus J into F1 upon F upon 1 minus J into F1 upon F minus K times AM upon 1 minus J into F1 upon F. Friends, let's remember this 1 minus J into F1 upon F, this 1 minus J into F1 upon F will cancel, and we get only AM upon this particular factor, that is 1 minus J into F1 upon F minus K times AM. Friends, let me divide this equation to the numerator as well as denominator by 1 minus K times AM, to this as well as to this. So that's why we can say ALF equal to AM upon 1 minus K times AM upon 1 minus J F1 upon F minus KM upon 1 minus KAM. Again, by taking LCM, one can write it, or this equation can be rearranged as AM upon 1 minus K times AM into bracket 1 minus K times AM minus J into F1 upon F. If we split it, we can write it as ALF is equal to AM upon 1 minus K times AM 1 minus K times AM minus J F1 upon F to be divided by 1 minus K times M. Same equation we have considered and we are simplifying it. AM upon 1 minus K times AM 1 minus J means this we are taking 1 minus KAM upon 1 minus KAM, it is 1 minus J into F1 upon F into 1 minus KAM. We are going to put now F1 dash is equal to F1 upon 1 minus K times M. Let me call this as equation number 4. In this equation, put f1 upon 1 minus k times am is equal to f1 dash. It is a new frequency in low frequency region after feedback. Let me call it as equation number 1. By substituting this, we can get it. ALF equal to am upon 1 minus k times am upon 1 minus z times f1 dash upon f. f1 dash is a new frequency, that remember. But am upon 1 minus k times am is amf. That is from how we have obtained this. We have obtained from this equation number 2. By using equation 2, we can write it ALF equal to AMF upon 1 minus Z times F1 dash upon F. Let me call it as equation number 5. This is we have written from equation number 2. For negative feedback, we are aware that feedback factor K is negative, that is minus 1. By putting K is equal to minus 1 in equation number 4, we get F1 dash is equal to F1 upon 1 plus KAM instead of minus. By putting K is equal to minus K, we can get it F1 dash is equal to F1 upon 1 plus K times AM. What this indicates? This indicates that F1 dash is less than F1. What is F1? F1 dash is the frequency, lower cutoff frequency in low frequency region after feedback, whereas F1 is the frequency in a low frequency region before feedback. Thus, after negative feedback, lower cutoff frequency decreases. This is half part of the proof we have considered. That is, the negative feedback decreases the lower cutoff frequency. Now let me consider the same amplifier, but we are working now in high frequency region. With its upper cutoff frequency F2 in a high frequency region at which the voltage gain falls to 0.707 times its mid frequency value of the voltage gain. Same definition. The voltage gain at any frequency f in a high frequency range is given as, instead of AL, now it is AH. AH is equal to AM upon, it is in high frequency region, so that's why we can write it 1 plus J into bracket F upon F2. That is equation number 6, where AM is again mid frequency gain. Now voltage gain in mid frequency and also in high frequency region after feedback is given as AMF is equal to AM upon 1 minus K times AM. Let me call it as equation number 7, which we have already considered. And AHF equal to AH upon 1 minus K times AH. Let me call it as equation number 8. These are same as that of equation number 2 and 3. Now putting the value of AH from equation number 6 in equation number 8, so as to get AHF equal to AM upon 1 plus Z times F upon F2 to be divided by 1 minus K times AM upon 1 plus Z into F upon F2, which is expected to be simplified further. So that is AHF equal to AM upon 1 plus Z into F upon F2 upon 1 minus K times AM Z into F upon F2 upon 1 minus Z into F upon F2. This 1 plus Z F upon F2 and this 1 plus Z upon Z into F upon F2 will cancel, so as to get AHF equal to AM upon 1 minus K times AM plus Z into F upon F2. Routinely divide to numerator as well as denominator by 1 minus K times AM, so as to get AHF is equal to AM upon 1 minus K times AM to be divided by 1 minus K AM plus Z into F upon F2 upon 1 minus K AM, which can be written as AM upon 1 minus K AM upon 1 minus K AM plus Z into F upon F2 upon 1 minus K AM, which is further simplified as AHF equal to AM upon 1 minus K times AM, 1 minus K times AM upon 1 minus K times AM, it comes to be 1 plus J into J upon F2 into bracket 1 minus K times AM. Now, put F2 into 1 minus K times AM as F2 dash. That is called as equation number 9. We are replacing F2 into bracket 1 minus K times AM by F2 dash. So that is F2 dash is equal to F2 into 1 minus K times AM. And by using equation 6, AM upon 1 minus K times AM, this is AHF. Therefore, we can write it AHF equal to AH upon 1 plus J times F into F2 dash. Let me call as equation number 1. But we are interested in equation number 9. Again, for negative feedback, K is negative. If K is negative, then F2 dash becomes equal to F2 into bracket 1 plus K times AM, which is represented here. So this indicates that F2 dash is greater than F2. What it indicates? It indicates that after feedback, upper cutoff frequency increases. So what we proved? The negative feedback increases the upper cutoff frequency. We have proved two things here. What we proved? We proved first thing, and that is after feedback lower cutoff frequency decreases, and after feedback upper cutoff frequency increases. Upper cutoff frequency increases, lower cutoff frequency increases, and we know that the difference between upper cutoff frequency and lower cutoff frequency is the bandwidth, and hence bandwidth increases. Thus we can say F1 dash decreases and F2 dash increases, which increases the bandwidth. Thus here we can say, by applying the negative feedback, in everywhere we have considered feedback factor K as a negative, indicating that we are applying the negative feedback. And we prove that after applying the negative feedback, the bandwidth of feedback amplifier naturally increases. So this is how we can prove that due to application of the negative feedback, there is increase in bandwidth. Friends, next time we will proceed for again one more advantages of negative feedback.